Welcome to the module. In this module we will see simple error detector. We will start with the simple error detector, which is nothing but a differential amplifier. When we see, right, so this is a differential amplifier circuit, right. One input will be connected to the R1 R2 pair resistor pair, other input is connected to the negative terminal, which is input of R3. So the output will be, so if you recall the working of differential amplifier, the output is nothing but V1 minus V2 into RF by R1. RF by R1. This is a case when if R1 is equal to R3 and R4 is equal to R2. Since in this case both R1 equal to R3, R1 equal to R2 equal to R3 is equal to R4. So RF and R1 values are same. So the gain of the system is 1. So the V0 is V1 minus V2. That is what even we required, right. When we recall our system, we do not have to apply any gain. Whatever the input I have, it has to be subtracted with the feedback signal and I have to get an output. That output we call it as an error, right. So in order to give that, I do not need any gain. So since I do not need any gain, I am using all the resistance of same value. So that may be the problem with instrumentation amplifier. So few instrumentation amplifiers will have a gain starts from 5. The commercially available monolithic instrumentation amplifier IC, the minimum the gain that will have is 5. So since it is not possible in this case, what we have to do is either we have to go with a high input impedance differential amplifier too, right. So I understood how exact. So we already know how does it works. So let me quickly look into the simulation. So in order to understand about the simulation, whether it is working fine or not, what we will take is we will take different points. So let us say I will take V1 and V2 and I will calculate V0. So V0, when you recall, it is nothing but V1 minus V2, the input that I am applying at this point and this point, right. So let me take one input as 10 V1 and another input as 2. So that means 100 degree and 20 degree. So what will be the V out? V out will be 10 minus 2, 8 volt. I should get an output as 8 volt, right. So this I am taking 8, this is 4. So V out will be 8 minus 4, 4 volt, 6, 6. So I will go with 8 in this case. I should get minus 2 volt, right, and 4 and 10 I should get minus 6 volt. Let me see whether I am getting these values if I design in a practical system. Now in order to understand about the gain, what we do is that we will in order to practically as well as theoretically to calculate the gain as well as the CMRR value of the system, what we can do is that we can apply same signals at V1 and V2 and we will see what is an output voltage we are getting. So we know that V out by the input voltage that we do, which we connect, is nothing but a gain of your system, right. When we connect the same signals, V1 plus V2 by 2 will be the common mode gain, because at this point we are taking V1 is equal to V2, we will get common mode gain. Now we will take different values of V1 and V2 and we will calculate what is an output and divided by V1 minus V2. This is nothing but our differential gain. Now if I want to calculate my CMRR, so CMRR is nothing but differential gain by common mode gain. So whatever the gain that I am getting, this is AC and this is AD, this divided by this if I do, I will get the CMRR of the circuit. We will see theoretically now and then we will compare with practical too. Excuse me. So to understand that, what I will do is that I will open a multisim. So let me create a circuit. So we are using multisim from so many experiments. So I do not have to explain about how exactly this works. and what are all the different functionalities and different system that it has. So, our only thing is that how do we implement it, that we will see. So, we will connect according to our input signal. So, what I will do is that I will take a 5 terminal, because the plus VCC and minus VCC are very much important to understand whether it goes to the saturation or not. So, that is the reason I am taking this value plus VCC and minus VCC2, and I will take some voltage sources, DC voltage, and I want to operate my system with 15 volts, changing settings to the input voltage to 15. So, positive is connected to the positive terminal and other terminal should be connected to the ground. So, I am connecting it to the ground. Now, I have to take another voltage source, because op amp has to be provided with a two different voltage sources. This is not a single source, we have to always take two sources, two independent sources basically. So, the negative of the power supply is connected to the negative terminal. So, since negative 12, since it is the amplitude is 12, since the negative is connected here, the value is 12 minus 12 volts. So, since we require minus 15, so this does our requirement. Now, what we have to do? We have to connect one resistor at this point. So, in order to not to have a mismatch between both this as well as our design in multisim, what I will do is that this is R1 I will consider, and this I will say 100K. In fact, you can also take any resistance value, but it should be all resistance whatever we use should be same one, but higher the resistances, right, more the input impedance of the system. More higher the resistances, more noise into the system. Noise is always proportional to the resistance value or resistance power for. So, that is the reason we have to moderately select between 10K to 100K, but 1K if I select is, even we can select 1K, but it will have slight loading effect to the previous stage of your system, loading effect on the previous stage of your system. If I go more than 1K, 100 ohms, it will have more loading effect on the system. So, in order to not to have that, we are considering somewhere around 10K to 100K. So, in this case I am considering 100K. So, I need to take one more resistor, and this is my R2. So, this R2 part is done. So, this part I have to connect it to the ground. So, the ground terminal I have taken, I am connecting it here. Okay. And this part should be connected to here, and this part also connected to the positive terminal. So, this is nothing but V1. So, I will take one more DC voltage source, connect at this point, right. What I will do is that this I will make it as, the name of this I will make it as V4, because V1 notation we are giving it for the input value. So, this I will make it as V1. Now, so V1 is ready. So, this value make it to 10, max is of 10 we are looking at. So, 10, other terminal should be connected to the ground. So, I am connecting it to the ground. So, this part is done. What is the other part? The negative feedback and the negative resistance at the negative terminal. So, I will take R3 resistor. So, this is what R3 that we are considering it, and one more resistor that I have to take, which is R4, which should be connected as a negative feedback. So, I am connecting one here, one more to this junction, and other terminal to the output voltage, right. So, this point I have to connect another voltage source. So, just a nomenclature, just I will just slightly change the naming of the system here. So, this I will name it as V5. So, whatever I take will be V2. So, I will take one more voltage source, this is V2 voltage source, and this part should be connected to the ground, Okay. So, this I will start from 2 volts. So, to understand what we have done, we have to apply 10 volts, 2 volts. Let me see. First we will see the differential gain, then we will do the gain of I think we have considered the resistance R3 R4 differently, and let me do the same experiments once again. So, I will take V1, connect it here, and this should be ground, making it as ground. So, this should start from 10 volts. So, let me take it to 10 volts. Then I should take one more voltage source. So, I need DC. So, I will take DC, connecting it here, and this should be ground. Now, so we will start from 10 volts and this value at 2 volts. So, what are all values we have considered? One is 10, other one is 2, other thing is 8. So, when we see what are all values that we have considered, 10 to 8 4 and 6 8 4 10. So, we know that this is 8, 10 and 2 8, 8 and 4 4, minus 2 minus 6. We will see what values we are getting for everything, then we will list it out. So, let me run. When I run it, we are getting output as 7.9958, 7.9958, whereas when the input is 8 volt, I am making this as 8 and this as 4 volts. So, what is the output we are getting? 3.995. So, approximately or almost close, because we always consider 3.99 as equivalent to 4. So, it is also giving 4. So, let me take it as 6, this should be 6 volt, and this value should be of 8 volt. When I see the value is minus 2.0041. So, almost same 0041. Now, this I will take it as 4 and this I am taking it as 10. So, what is the value we are getting? Minus 6.0040. So, we got all the values. We will also take V1 and V2 as same values and we will see how much we are getting. So, we will take V1 as 5 volt one value and V2 also as a 5 volt other value. So, when V1 is 5 volt and V2 is 5 volts, actually the actual voltage should be 0, but as I told you it will be always at millivolt. So, when we see it is somewhere around minus 4.0811 millivolt. So, what about for other value? So, let me take the value somewhere around 10 volt and this also at 10 volt, should be almost same. Yeah, see when we see 10 and 10, actually the value should be 0, but we got minus 4.1323 millivolt. Now, let me put everything in graph and we will put everything in our slide and let us see what we get, what will be the CMRR value, right. And so, when we recall what values we got, V1, V2, actual output. So, actual output is nothing but V1 minus V2. So, here I will write V1 minus V2, no gain because 100 by 100 will be 100k by 100k, it is 0, and consider this is simulation, V naught of simulation, output voltage at simulation, what is the value we are getting. So, V1 we have considered 10, this is 2. So, what is the value? 8 we got, right. When we do manual calculation it is 8. What about the simulation we got 7.995 volt. Then this is 8, this is also 4, this we got 4, So, whereas this is 3.995. When we apply 6 and 8 as an input voltage, we got minus 2, even here we got minus 2.004. What about here? 4 and 10, we got minus 6 when we calculate theoretical, and simulation we got 004, minus 6.004. And we have also done other experiments when both inputs are same, which are nothing but common mode signals, but actually speaking the output should be 0, but we are not getting 0, we are getting some value of 0.811 milli, and even it is almost same even when I am taking different voltage value of 10 and 10, which is of minus 4.1323 milli. Now, if I want to calculate CMRR, first I should know the calculation of differential gain, then I have to calculate common mode gain. But how do we do differential gain? So, the differential gain is nothing but output voltage that we are getting divided by common mode signal, divided by differential input signal V1 minus V2. Now, when we see the theoretical value, so this is 8 for the first one and 8, this is 1. So, we are getting differential gain as 1, right. So, even for the second case, 4 divided by 8 minus 4, 4, 1. So, whatever, no matter what, for this particular set of values we will get the gain as 1 theoretically. What about the practical? This is theoretical. So, AD simulation, when we see the value is V0, V0 is 7.995 divided by 10 minus 2, 8. So, when I calculate, I am taking calci, 7.995 divided by 8, 0.999, which is almost equal to 1, no matter what. I will take the next value too, I will take calci. So, 3.995, so 3.995 divided by 8 minus 4, 4, 0.998. So, almost equal to 1, right. We are getting almost everything equal to 1. Now, what about AC? Theoretically it should be 0, but practically when I see, simulation wise when I see, the value is minus 4.0. So, how do we calculate? First let me write the formula, output voltage by common mode signal. So, V1 plus V2 by 2. So, what is V0? Minus 4.0811 milli divided by 5 plus 5 by 2, which is nothing but 10 by 2, again this is 5. So, minus 4.081 milli divided by 5. The value is, and I take a calci, 4.081 divided by 5, 0.81, how much? 62 milli, 0.8162 milli. So, that means the value is 816. No volt, because volt by volt will be cancelled, right, 0.816 milli or 816.2. Now, if I want to calculate CMRR, theoretical when I see, it should be AD by AC 1 divided by 0, which is infinity, but practically is it the same? Let me see, which is differential gain, which is of 0.999 or 998 or 0.99 divided by 816.2. So, the value is, let me take a calci, 0.99 divided by 816.2, which is 0.0012. 0.0012. Now, if I want to calculate in dB, 20 log 0.0012. So, I will write it down here itself, 20 log 0.0012, which is equal to So, I will take Cal C once again 0.0012 log into 20. So, which is 58.416 dB. Why I am eliminating minus? Because CMRR should be always mod of, or even in this case here we have a negative, and when we calculate minus we are getting minus is becoming positive, but CMRR generally mod of AD by AC. So, which is 58.4 dB for this particular type of op amp, right. Suppose if we are taking different op amp, I do not know what op amp that we have considered in the simulation, what make that we have considered. So, we have simply used the op amp that is available there, right. So, this is how we generally calculate the dB of our differential amplifier, but moreover since we are not going to apply almost a common mode signal, but even if we apply we are getting somewhere in the milli, since it is negligible. So, we can simply go with a difference amplifier itself. Now, how about for instrumentation amplifier? Why do not we look into that? So, what I will do is that I will take one more slide. If you recall the working of an instrumentation amplifier, so it will be somewhere we will be taking 3 op amp plus minus one more op amp plus minus, right, resistor combination. So, this is R, this is R, this is Rg if I take, minus and plus connecting here, this here and this here. If I say this is V1, this is V2, right, and I should also have to have a differential amplifier here plus minus, oh sorry, this is Rg, the output should be connected one here, one more here and one more here, one more here. So, 100K, 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 4 resistance here, 1K, 1K. If I take the V naught, so when we see V naught is nothing but 1 plus, generally V naught value is 1 plus 2 R by Rg into V1 minus V2 is the equation. Just look into the instrumentation amplifier circuit, you will understand. Now, in this case what we do is that we will design the same thing and we will see for different values of V1, V2. Now, I will say this is VO1, this is VO2. What are the values of VO1 we are getting, what we are getting for VO2 and what about V0. So, I will take Rg as 2K. So, if I take Rg as 2K, the gain will be 1 plus 2 into 1K divided by Rg 2K. So, this is this one. So, the gain is 2, right, the gain of the system is 2. So, we will see what is the gain of the system even theoretically, and so theoretically we have calculated which is 2, we will see with simulation. Now, so to the same circuit what I will do is that I will take few more op amps. So, let me keep this aside. Okay. I will take simply 3 terminal op amps, it is more than enough. Okay. So, I have to choose different resistors, one here, one more here and one more here. Now, the output has to be connected at this point and negative terminal should be connected here, this 2 here, and this 2 here, whereas the negative terminal should be connected here. This is my V1, whereas this is my V2. This has to be connected. So, all the required connections are made. Let me run. So, this is VO1, this is VO2, this is V0. So, I will take 2 more probes connect at this point, 1 more probe at this point, which gives you V1, V2. When I run it, yes. So, when we see both are at 10, so we are getting minus 4.1323 milli. So, let me change 10 and 2, 10 and 2. So, 10 and 2, how much we are getting? At this point we are getting 12, this point we are getting minus 3.0152. Now, I will see. So, V1, V2, VO1, VO2 and V0. V1 is 10, V2 we are applying 2, V1 we are getting 12 and VO2 is minus 3, V0 is 15, right. So, 10 minus 2 is how much? 8. 8 into gain of 2, 16, approximately 15 we are getting. Because why 15? It has gone to the saturation because of the voltage. So, what I will do is that I will decrease to 4. Now, second input is 10 and 4, 10 minus 4 is somewhere around 6, 6 into 2 12, I should get an output of 12. So, we are getting 12.056, right. Then, so this I will increase 8, this V2 to 4. Let me take this as 8 and 4. So, 8 minus 4, the theoretical value should be 4 and 4 into 2. So, but we are getting 11.996. Now, what I will do is that V1 I will make it as 4, V2 as 8, this 2 4, this I will make it as 8. How much we should get? 4 and 8 and 4, 4 and 8 we got minus 12.004. Let me apply the same signal, which is of 4 and 4 or 5 and 5, because that is the signal that we have used, 5 and 5. So, I got somewhere around, and apply both 5 and 5, I got minus 4.0811 milli. So, this way we can even construct instrumentation amplifier and we can calculate our CMRR value for the instrumentation amplifier too, right. Now, we will see what is our actual thing, right. So, we have calculated and theoretically we got the gain of 1. So, theoretically as well as we got practically we got gain as 1 and the CMRR as 58.4 dB. So, no problem with this dB for us. So, we can go ahead with this differential amplifier too.